Let's consider the runtime of another recursive function. This one's called binary search. Now this is a really important idea. I'm assuming you've probably actually seen it, but if not, I think it'll be pretty easy to follow. And the way it works is we have an array of items that is all in sorted order. That's very important. And we have a key that we want to find. So in this case, our key is a number 33, and we want to search for it in this array. So how it works is we start by looking in the middle of the array and saying, is that our key? And if we find that the key is too small compared to the middle, or if it's smaller than the middle, then we're only going to consider the left side of the array, which is the case here. We know that it couldn't possibly be over here. If 33 is in the list, it's definitely not going to be bigger than 53. So we look on the left side, and to do that, the way we're going to represent the fact that we're only looking on the left side, we're going to move this high pointer to the position just to the left of the old middle. So in this case, it is now 6. So you can think of low and high as the bookends of all the things we care about in the array. Okay, so looking again, we now need to look in the middle. So in the middle between 0 and 6 is 3. So we compare 33 and 25. In this case, the key is too large, so we'll look on the right side. And so that means moving the low pointer up. And so we'll repeat this process until we either find what we're looking for or we run out of places to look. Now, just to make a note real quick, there's a cute little formula to determine how many items are still in play, which is to subtract low from high and then add 1, and that gives us 3. Just because that'll be useful to us later, I wanted to point it out now. Okay, so now we look in the middle again, and we say, what do we have? 43. Well, in this case, the key is too small, so we'll go left. And in this case, the low, the mid, and the high are all 33, and this is great because we actually see the item we want, and we have found it. Now, sometimes it's actually faster than that. Maybe the item you're looking for is directly in the middle, in which case you're done instantly. In this case, we actually had to hop around a few times. So let's see what it looks like when the item we're looking for is not in the list. And in this case, I also happen to have chosen an array of even length because it'll introduce the important issue of what happens when the array is not exactly, there's no exact middle. So in this case, we have 10 items. We look at position 4 in this case, and we find that 49 is less than. Okay, so we'll only consider these 4. Now, something that wasn't totally obvious with 10 is there was no exact middle. Here, we have 4 items, as you can see here. And again, there's no exact middle. The exact middle would be 1.5. So we actually have to do a tiebreaker. And the way we'll break our ties is we'll always round down. So in this case, I'll pick position 1. And in this case, I compare 49 to 20. 49 is too big, so we'll look on the right. Okay, again, we have 2 items to look at. We would like to look at position 2.5, but there isn't a position 2.5. So we'll round down, and we'll take position 2. In this case, it's still too large. We now look at 40. That's the only place left. And in this case, we find that it's not 49, so we have no more items to consider, and it turns out there is no 49 in the list. So that's what binary search looks like. So binary search is interesting because it's a really elementary and very important algorithm, but also a very challenging one to implement properly. If you look in John Bentley's book, Programming Pearls, he says the idea was originally published in 1946. Of course, it was known to people before that for searching, but this is the first time it was published in an academic journal in the context we would recognize it as today. And according to John Bentley, the first correct implementation was not until 1962, because it's actually quite tricky to get all the details right. Now, at the bottom of the screen, you can actually see an implementation of binary search. This is the older Java implementation of binary search, similar to it. There's actually a very, very subtle bug in this code that was in the official Java binary search until 2006. If you're curious about what the tiny bug is, you can check out this link, but I won't say any more about it. In fact, you don't even need to look at this code as we work through these examples. All I want you to do is have a mental picture of what binary search looks like, and then we'll run it, analyze its runtime from there. Okay, so we'll start by having you try to find the runtime of binary search intuitively. And so what I'd like you to do is consider, we have n items. I put them here. I mean, it doesn't really matter how many there are. Consider an array, and let's consider the worst case runtime, where either the item is in the last place we look or not in the array at all. And tell me, as the array grows, what is the order of growth of the runtime going to be? Is it 1 log n log n, or 2 to the n? Just use your intuition. However you want to do it, come up with an answer you're happy with. Okay, so log n is the correct intuitive answer, And the way to think about this is to say, well, initially we have n items, but then after we've done one step, we have n over 2 items roughly, then we have n over 4 items roughly, and then n over 8 items roughly, until we get down to having just one. And so we could think about it as we're cutting the array in half over and over and over until we have just one item left. So it's just a simple math problem at this point where we say, if C is the number of calls to binary search, if that's our cost model, then we're solving for basically how many times do you have your array initially of size n, how many times do you cut it in half, C, before you get down to one item. Now we do just a tiny bit of algebra, and we'll get that C is equal to log base 2 of n. So that's the intuitive approach. Now, if you're looking very carefully, you'll notice that it's not exactly halving. It's close to halving, but it's not exactly halving. And so in the next video, what we'll do is be very careful to prove this in a more rigorous way than just trusting our intuition. But for the most part, this kind of argument actually is pretty good for our purposes as data structures understanders as opposed to mathematicians. But just to make sure we really get it, let's be more rigorous in the next video.